Okay, and there you go. All right, hey guys. I was supposed to do this a long time ago, and I just never got around to it. So I thought I'd make a video just to kind of show you the where I stand on the plugin, and just kind of the functions and tools that are available if you need them, and just kind of the direction I'm going, just as an update. So I'll go ahead and I'll just start by running the plugin, and you can see you won't be able to see this on Dijkstra, but it's running on locally, so you can get the actual virtual machine. You don't have to remote into it. You can it just pops up a new window, and you can see the plugin runs in the console where Panda was launched, or QEMU was launched, and it just outputs information here, and it also has a file that it logs everything to as well. So I'll let this run for a little bit, and it should start like populating with some information. In the meantime, I'm just going to get into the code and kind of show you what the plugin can do. The first thing I want to mention is the logging functions that you see. So you can see, okay, yeah, so you can see it's starting to do stuff here. I'll go ahead and I'll kill it so we don't flood the console, but the logging you can do, so this logging is what would you call that? It's available in Panda. It gets loaded in with the Panda source code. So anywhere you see a logging function, you have access to that inside Panda and any of QEMU's files that Panda touches. So that's a nice little tidbit if you're working in like Panda code and you want to log something and have it output to the console and save to a file just as backup, and it will tell you that information, and it will reflect too. If you log inside Panda, it will tell you Panda, what Panda file the log was generated from. So those are just nice features that are available if you need them. To use, I guess I'll just start with the logging then. To use the logging, it's pretty straightforward. There's like 3 ways you can call it. So one is just kind of to directly just say log and then give it a string, and it will log that string just as a normal log. If you want to specify what it is, so like right now these are all just normal logs, but sometimes there's like errors or warnings that pop up. See, here's a warning. So if you want to specify a different type of log, that's pretty easy too. You just say log, I don't know if, so like log, and then you give it the prefix. So there's error, warning, a log prefix, which is default, and then you give it a string. And if you want to do like some printf stuff, you call logf. That requires a prefix, a format string, and then just variable arguments for whatever you're printing. And it uses like string printf for logf and stuff like that. So that should take care of everything you need for logging. I'll just jump right into the functions and kind of show you what's available. Not everything is fully implemented because working on this project, it was like at first the goal was just to dump memory reads, but Eugene's system already does that well, so there's kind of no reason to do that. So I just kind of started, I have like some starts of that, but then I stopped working on them and started working in other areas. So that will kind of be reflected in this functions. I didn't want to delete anything just because I don't know what I'll need yet, or what we'll need yet. So this get host TSC returns the timestamp counter of the actual host system running QEMU, and that just calls an assembly command. So this is pretty accurate. Turns out, I didn't know this at the time, but it turns out that the guest TSC is the same as the host TSC. It's just offset by some fixed amount when QEMU loads. So you could also use this to get the guest TSC very quickly. Just know that it's not offset, so you'd have to account for that somehow. It's quick because it's assembly, right? If you don't care about quickness though, and I wouldn't, because I mean, it's not super time critical. You could just call get guest TSC, and you know, down here there's the save function. But you just call get guest TSC, and this calls into key. Yeah, I think it calls into QEMU. This is part of QEMU. Yeah, QEMU. And this will just give you the offset TSC value. As a warning, you do not want to access TSC directly from this CPU state, because even though there's a TSC register, it's only used with virtualization. And Panda can't run for the memory. Well, even I think my callback requires, yeah, no virtualization. So Panda, the system, the Panda can't run with virtualization enabled. It has to go through the tiny code generator. So if you disable that, the TSC register is still there. It's just always 0. So you want to make sure that you're calling this. You're not accessing it directly. Okay, so that's just like some timing information. If you're wondering how you get this x86 CPU, it's just you get it from this normal or this x86 state. You get it from the normal CPU state. It's just to use it, I wrote a little macro up here. I think that's where is it? It's called like get, yeah, see get x, you just call get x86, and it just does this cast for you and like dereference for you. So it's kind of like, so you don't have to remember what you're doing every time. You just call get x86, give it a CPU pointer, and this is a pointer to the CPU state, and then it will return to you the x86 CPU. If you want to get the actual CPU, you call this. This calls into, I think, QEMU, and it's again like a cast thing, but I didn't feel like I got this far into the source code, and it's like, oh great, I can just call that. You know, I don't have to work anymore. So it's again just a direct cast. So it's kind of like, I don't want to say free, but it's almost free, right? In fact, it might be, I don't know if this is dereference or not. I think there is a dereference, so it's not quite free, but you know, it's pretty cheap to convert between the two. So you can, yeah, that's available. This threading ID stuff, honestly, I haven't tested, so I can't really speak too much about how accurate it is or if it works, or what it is even really giving you, if it gives you anything at all. It's there. I thought it was something to look into. In fact, maybe we'll put a little comment and we'll say like, look into this, right? But we don't need it. I mean, hello, thank you. Oh, it's okay. I mean, I don't use it, or I haven't needed it yet, so I haven't looked into it. So just be careful if you're using that. I think it's supposed to give you like what, if you have like a multi-core system, it gives you the current CPU's like execution core number. So like if you had a 4-core system, you'd have 4 threads. I think that's what it's doing. Yeah, these aren't like operating system threads. I don't believe. Okay. Oh, and just for reference, I did test out the Panda plugin with multi-core. So like you can't use virtualization, but I tried it with multi-cores, and it looks like it can do multi-core. But for simplicity and just for sanity, I'm still running it in 1 core just for now. So the thread ID would ideally be the same, if you know, just always 1 or 0. I don't know what they start at. All right, this write MEMS mid file. This is just the file format I was working in for the plugin. You don't really need to use this. You wouldn't really need to use this directly. Because I write helpers to do simpler things, but basically the idea of the format is like everything's a mid. You have like this one structure right here called a mid, and a mid carries some like just critical data that you'd want to log no matter what. So like what type of information you're logging, what time you logged it at from the host. Again, I didn't realize these were offset. So what time you log it as a guest, you probably only need the guest TSC then. You know, your what thread it was, what CPU was that was running, and then you have some some information about your current thing that you're logging to, and this is union together. It may don't be quiet. This okay. Has some extra information. So like if you're logging a string, you can access like mid.mess and modify the string pointer, or if it's an error, you can access it .error and you modify that. So all this stuff gets kind of like it's like kind of all it's union together, and you can also access it with info. So you can do like info.mess, just trying to make it easy or clear no matter what type of mid you're dealing with. And then you eventually hand this over to this write mid, and write mid basically reads in that type, figures out what it's actually supposed to log from that structure, and dumps it into the file just to keep the file size down and to keep everything kind of uniform. So obviously mid files the structure is kind of clunky, so there's generate mid skeleton, which will take in a type, and you give the CPU and it will generate you kind of an empty mid thing. And then you input into that mid whatever you're doing, and then you give it to write mid. So like for instance, if I wanted to write a message, here's a helper function for writing a message. You give it a message, a character string, you give it the CPU, or if you don't give it the CPU, it's just empty, like it wasn't known at the time. It creates that mid skeleton, and then it it writes into the message of that skeleton the message, and then it writes it. So like that's the idea of that union, is you can say mid.message, and now it's a message mid, right? Or if it's an error, you can say mid.error, now it's an error mid. If it's a binary data, you can write it to the binary data. So it's just supposed to make it easier to use. Obviously it looks really ugly in the header file, but when you're actually using it, it tries not to be ugly. And these helper functions too try to abstract you a little bit further away from it too, so you can just say like, what's the message, and it will log a message. You don't have to know the workings of it. Same thing with these log functions. They're just supposed to be simple and easy to use. Error, again, this is like deprecated, I guess you'd call it. The ideal, like realistically, when I first wrote the log function, I didn't have like the error prefix. I just had like log prefix, so it didn't have a prefix, right? So you couldn't specify like what type of log it was. So that's why error was like kind of like a reserved thing. And then I started wanting to log warnings, so I like added the warning prefix, and then it's like, well, like just add the error prefix. And so I added the error prefix, and now this is kind of useless. The idea is maybe this would turn into like a panic. If you had to like exit the plugin, you could just call like this, like, and it would panic the plugin. Or maybe all of Panda or QEMU, I don't know. But this would be like a hard error, if anything. But right now it's deprecated. I wouldn't really use it. Just use the logging function. printMIDHeader. Okay, so yeah, then we get into kind of just debugging stuff. Obviously, this is my own stuff. Just so I was making sure I was writing these the mid files right. But down below, we've got some more logging for just like actual like internal CPU stuff that gives you access to what the CPU is doing, or kind of a window into what the operating system's doing. So printMIDHeader just takes in a mid header and prints it in like some human readable form, right? And you can see that when it first creates the mid file, it just prints out some stuff so you know what's going on. Oh, another thing to mention, this host TSC frequency will, okay, first this guest TSC frequency is garbage. This is wrong. I know what's wrong. So this is not what it's running at. The guest frequency is the same as the host frequency. The host frequency should be 2.8 gigahertz. So it should be 2.80000. The reason why this is off is because if you're not root, I don't think there's a way you can really get that. Or no, I did find a way that you can get the frequency. Yeah, there's a way you can get the actual 2.8 gigahertz even if you're not root. That's right. I just haven't implemented it yet. And the reason I haven't implemented it is because I don't use it. So I just haven't gotten around to fixing it. So just be a little bit cautious. If you are reading the guest frequency, don't listen to it. It's the host frequency. and this number here is going to be an approximation of what the actual value is. So like 2.82 gigahertz is pretty close to 2.8 gigahertz. The reason why it's an approximation is because this like actually just does a like an int 16 overflow and weights and counts like how many time increments have passed with a Linux timer, and then like divides down the TSC to get this value. So it's not perfect because the Linux timer isn't perfect, right? It has a granularity. The TSC is kind of the lowest granularity you can get, so there's always going to be some discrepancy between the two. The start frequency though, or the start TSC, this is the actual TSC for the host. The guest TSC would start at 0, right? Anyway, so just warning with that. But yeah, so there you can see that's what these debugging functions look like too. If you call them, they'll tell you what they are, and then they'll just dump some information, and you can read that and interpret it. It also writes these don't. If you call a print, it does not write it to the log. This is just to the console. If you call a write, it logs it to. It writes it to the console and also writes it to a file. So print is just to get like verbose info out, not to log it. Create mid file, again, don't really have to worry about this. It's pretty straight. And I put in a ton of like notes in here telling you that yeah, these things are wrong, right? We have to fix those, but I'm just too lazy. Don't really have to use this really. In fact, you don't really even need a mid function. The log functions will work if there's no mid function. Or if there's no mid file, the log functions will still work. They just won't output to the mid file. In write mid, I think same thing. Won't I think it's checked. Don't quote me on that, but I think you can. No, write mid will crash. I think if there's no mid, maybe I don't know. I don't remember. You could look at the code. All right. This is stuff I was working on, which this is like memory stuff. So again, use Eugene's system. He's got it figured out, so just use that. So I didn't work on that. CPUMemoryMode is really nice. It kind of just tells you what the CPU, if it's in like long mode, if it's in like what paging mode, stuff like that. This is just, again, verbose memory. When the x86 CPU starts up, it's like in this real mode, and it's the kernel's job to kind of transition into like long mode for 64-bit Linux. So this is kind of was useful for debugging, just where, like in very early boot, where the what the state of the CPU is, and like you can kind of pinpoint what the kernel's doing by looking at this in very early boot. So like those times when the CR3 registers are 0, you can figure it out. It's like, oh, because they're not using paging, and stuff like that. So this is kind of nice. But once the CPU is running, the CPU state will be locked into like long mode, and it won't change once Linux is running. printCPURegs is kind of nice. Just anytime you need it, what it does is just dumps all of the registers. These are 64-bit registers if you're in 64-bit mode. Even though they say EAX, they'll just be like RAX, right? And it does dump the full 64 bits. So you can just say like, what are the control registers? What are my flag registers? What are my actual like registers? And just to kind of debug the CPU that way. So this function is also really handy. One thing to note, if you do want to get just the flag registers, you cannot access the flag registers directly from the x86 state. You have to go through this compute eflags. That's because like QEMU caches like the flags when they're doing like the code translation, and so like if it's not if this gets called when it's not quite at the end of a translation block, if it's like inside of a translation block, this flag will just be garbage. So to actually get the flag, you have to call the CPU compute eflags, and this will update take the cache and update it to reflect the actual flag. So don't call the flag registers directly, because they'll be out of date like 99% of the time. Okay. Print CPU model specific registers. This is like tells you like this is the targets. This is basically the addresses of like syscall and sysenter callbacks. So like this was I don't think you'll need it, but it was helpful for me for trying to figure out how syscall works. Print CPU segment cache. It doesn't. It prints. So like x86 CPUs, they cache segments, so they don't have to keep going out to memory. And this prints out one of those. Or no. Sorry. Yeah, this prints out the base addresses of all of those caches. So like at any given time, your CPU has 6 caches in it, and then this KGB, which I'll talk about in a little bit. These are like the current code segment, the current stack segment, and stuff like that. So they're not really that important. The reason is because when you're in 64-bit mode, all of these are forced to 0. So these will always be 0. There is a couple of exceptions, like this code segment might be slightly different if they're doing like if the Linux kernel is doing something tricky with like task structures and stuff like that, but Linux doesn't, so this will be 0. But the important one is this KGB and this GSB segment. So the you can kind of, these are all forced to 0. But these down here are up to the operating system to do whatever they want with them. So normally FSB is reserved for your program. So your user space can use FSB. And GSB is reserved for like thread specific thing. I'm trying to be okay. GSB can be used by the user, but it's also used by the kernel, and the kernel specifically uses KGB, which is not really, doesn't have a name. It's just the GS register for the kernel. So maybe it should be KGS. Actually, maybe it should be KGS. That's a good point. So this is the kernel's GS pointer, and they use this for like offsetting. Oh man, I'm going on a offsetting memory accesses when they're in the kernel mode. This is, long story short, in Linux, this gets translated down into the base pointer for the kernel stack for a given CPU. So if you have like a 1-core CPU, there's only one base stack for that CPU, and this is what it's going to be, and this is the base for like everything. So like the how do I say this, like when you launch a program, each program gets its own little kernel stack, but this is the base for like the first program that launches. So like if you have three processes running on a single CPU, you'll have like you'll have 3 stacks on that CPU. This is the very first one where they all start. So this is kind of important like this. This is like actually like the interrupt stack, I think it is loaded there or something like that. So this is good for locating kernel memory. Okay, long story short. Print segment cache is actually just, the segments are really ugly. They're full of like different things, and this just kind of prints a segment in a human readable form. They're not just an address. If you actually look down here at a segment, you can see like there's like a low base address, and then there's a high base address, and then there's like, they're all kind of scattered around. So print segment cache just kind of tells you the things inside of a segment. And there's also, I think, I don't want to go too far down here. Print segment description, again, takes in one of those segments and kind of decomposes them for you even more. Okay. You shouldn't be messing with segments. I mean, x86, I don't even think uses segments that much. 32-bit Linux doesn't use segments that much, and segments are basically not used in 64-bit mode, except for like this very low-level switching between user and kernel space. Okay, CPURegs is pretty straightforward. This just is the same thing. It just casts it for you, so you can call printCPURegs with the CPU or an x86 CPU, just because that's like the most probably used one. GetRing is nice. It tells you your current execution privilege level of the CPU. So if it's like ring 3, it's the user space. If it's ring 0, it's the kernel space, and you can call this ring string, which will kind of translate that for you. So you can translate that into a string if you want. The only thing to be cautious about is this ring. So this ring is always right. Ring will tell you what state the CPU's in. That doesn't necessarily mean that like your stack pointers are valid yet. x86 requires the operating system to be responsible for handling, in most cases, for handling the stack pointers and stuff like that. So when you call, like, you could get into a situation, and I was in a situation where I was in the kernel's ring, but my stack pointer was still the user's stack pointer. It wasn't updated to reflect the kernel stack pointer. So like, just because you're in ring 0 doesn't necessarily mean that all of the registers are updated to reflect the kernel's registers. The register, things like your flag registers are handled for you, and stuff like that. But you just use it with 99% of the time it will be right, because 99% of the time you won't be like right on that border transitioning from user into kernel. But if you are getting weird things, just keep that in mind. If you want to check real quick if your memory is kernel memory or user memory, an easy way to do that is just to mask the upper 4 bits. Linux is nice if it's the upper 4 bits are FFFF, it's kernel memory. If the upper 4 bits are 0000, it's user memory. And x86 only allows those 2 prefixes for the virtual memory addresses. So it's one of those 2, and you're either kernel or user mode. So, yep. Rings in the middle, I don't think they really ever use, so you don't have to worry about those. Okay, printCPURing just does what it says. printCPU basically just dumps everything it can about a CPU, which is nice. getTSS returns a task segment struct, so this is kind of that like the very small amount of segments that you have to know, or you don't have to know, but like that Linux actually uses is this TSS struct, and that's how it communicates, like how it saves where the kernel's stack pointer is when it's switching from kernel to user mode, and then when you switch from user to kernel mode, it loads in that kernel stack pointer from this TSS thing. So getTSS has like a couple interrupt, you can see them down here. Yeah, there's like a couple pointers that it saves, stack pointers that it saves, and a couple of like interrupt vectors that it saves as well. The RSP0 is, I'm kind of rusty on this. RSP1 is the actual top of the stack. RSP0 is something else. It's there, but I haven't been able to translate it properly. Like RSP0 or RSP1002. Yeah, I think RSP0, I wasn't quite able to identify what it was. Like, it just, like, I couldn't use it. RSP1 was the top of the stack, and RSP2 is top of the kernel stack for the current process, not the base kernel stack. That's what the KGS is. This is the top of the kernel stack for the current process, and then RSP2 is reserved for the sysenter location, something like that. Which you don't have to worry about that. But if you're curious, I think they comment them somewhere. I probably do, because I'm going to forget. and I'll need a comment. If I haven't commented them, I should comment it. Okay, so this is kind of an interesting thing. So Linux, the newer kernel support page table isolation to kind of combat meltdown. And what that does is it basically means that it maps memory spaces two ways. There's a map. Sorry. There's a map which is given to the user, which doesn't have like kernel sensitive stuff or kernel code kind of mapped to it. So if the user tries to read kernel code, it can't because it's not mapped. And then it also has a kernel mapping of that program, which does allow for kernel memory accesses, right? And what page table isolation does is whenever the kernel is trying to do something, it goes into this kernel mode, right, where it can see everything, and then before it gives control back to the user space, it takes that privilege away, okay? And what that ends up looking like is a masking of there's 2 bits on the CR3 registers for the users that get turned off when you enter into the kernel mode. And depending on, I don't know, I haven't read the source code that much. I didn't feel like learning too much about Meltdown. Depending on something, it sets either one or both of those bits back on. Or it might be exclusive. Honestly, I don't know. So instead of trying to figure out which bit to turn on, it just this system just caches the user CR3, and it can kind of like toggle back and forth between the two. So if you're, long story short, if you're trying to read kernel memory, like virtual kernel memory, you want to make sure you call load kernel CR3 before you read it, and then when you're done reading it, make sure you call load user CR3, because this actually affects the CR3 register, and like if it's in user space, you don't want to be giving the user, I mean, all the programs should still run the same because they're the same mappings, but like ideally, like we're changing something that the operating system hasn't done. So yeah, you'd want to use them in pairs. If page table isolation is not enabled, which it's not enabled by default, these things do nothing. So that's nice. But you should still call them and they'll do nothing, right? Print segment description again. Oh my gosh, just prints out those segment descriptions. They're really ugly and long. I did need this, which is why I wrote it. Everything I wrote, I used, except for like that threading stuff up top. So like, you might need this for whatever reason, and it does give you a lot of information. But it's you probably won't need it. This, I do want to say, if you do use this though, there's like system segments. There's like that's used for TSC and stuff like that. Those segments I haven't given you like extended information about, because I just got tired of like programming this and I didn't really need it. I didn't need it. I needed these. I didn't need those, right? So if you have to know more information, I linked to the actual manual where they tell you more information about it. And if you want, I can program that in, but again, I didn't need it. I don't think you'll need it. And Linux doesn't really even work with task segments or system segments often. The only one that they use is like task segments from it, and even then they only load in like one task segments for the per CPU core. So it is very rare that you'd need that. Segment DT lookup actually takes in the address of a segment base, and it loads in the segment from that base. So this kind of gets used in tandem with this print segment description. Look up a segment so you know how to like what's going on. Okay, probably don't need that though. Kernel Stack base is probably the most. This is where I'm working on. You can tell by all the comments. This is kind of where I'm working on right now. And this lets you get the base pointer for their current process, your kernel base pointer for the current process. Yeah, basically that's all it does. And it was a pain to figure that out, but it works. Okay. The kernel Stack is 16K and 64-bit Linux. It's 4K and 32-bit Linux. And that's reflected in this kernel stack size. So if, like, over here in the header, if you toggle between the two, page size is fixed to 4K, but if you toggle between the two, you know, it will adjust, and so it should still work. Okay, dump kernel stack just dumps the kernel stack to a MEMID file, so you can debug it later. And then these are kind of the two callbacks to see, like, what process. Sorry, that's rude. What process is being executed, and who's starting that execution and stuff like that. So when when a user space program is trying to execute another program, no matter how it does it, it will get sent through this EXECVE callback. Okay, and this EXECVE callback will pull the file name for you, and it will tell you the file name of the program that's being requested to start. This works in tandem with the return callback, I guess I'll just tell you now. When you enter this, you're the calling program, right? Or the caller, right? So, like, if Bash is trying to run ls, when you enter this EXECVE callback, your CR3 registers and stuff like that will be for Bash. The string that it will give you, your file name, will be for ls. Okay. When you enter into EXECVE return, it's after your process has had its, like, insides replaced with ls, and your CR3 register now reflects ls's CR3 register, and everything reflects ls. When you enter into this, your user mode. When you enter into this, your user mode. So it's after the kernel gets done with swapping your guts out. Okay, and you're both in user mode in both cases. So that's nice. So now you know what the calling program is, what the caller is, and what the child is. Okay, so that's about that. There's that. These are things that Eugene system handles, so I don't implement them, but this is where you'd hook for listening to like virtual physical reads and stuff like that. When you this function right here, like I said, the segment translation blocks, or not the segment, jeez, I'm getting confused now. The table translation blocks for the tiny code generator that Kimu uses, those blocks don't update the instruction pointer until after they're done with a whole translation block. So if you're inside a translation block, your instruction pointer will not be right until it will be an old instruction pointer until you leave the instruction block or the translation block. Then it will be your new instruction pointer. So enable precise PC basically, basically forces Panda to, forces Kimu to update that instruction pointer inside of the translation block too. So that gives you more accurate things. Now, a warning. I don't know how reliable this is. From my testing of it, it seems perfectly reliable. Like, I haven't had it do anything suspicious. It looks like it's, it's never the same. It's always incrementing. It looks good. The reason why I say that, though, is this is updates in the same area that the, like, instruction callback gets updated, and I was missing basically all of, like, well, not all of, but I was missing a ton of syscall instructions when I was hooking them that way. So with the instruction callback, so this might be missing some updates. Just a warning. So EIP, your instruction pointer, looks reliable, but I wouldn't, if you have to use it, like, we should probably do some more research and figure out, like, how reliable it is. Okay, and yeah, that's the whole plugin walkthrough. Really long-winded. I'll probably put, like, links in the video so you can just kind of, like, jump ahead to different things. But yeah, that's it. To give you, I was running right here, so right now it doesn't do much. What it does is it just, when a program is being executed, it will tell you who the caller of that program is, what the CR3 register is. So for instance, here's self-exe is executing a program. Oh, I'm sorry. This is the very first execution, so I actually don't know who this is, but this is low level. Maybe it's grub. It might be grub or something like that. Executing this program. When you enter this return, you can see that you're in fact, yeah, okay. So these CR3 values are different, right? So this is like the caller CR3 value, and this is the child's or callee, I think, I don't know, whatever, CR3 number, and this is the kernel stack pointer where it's at, and this right here is the physical address for this virtual address, so you can see where it is in physical memory too. And yeah, basically this that's all this does right now, is it dumps these kernel stacks, and I'll tell you why in a little bit. But you can see kind of what goes on. So it's like, this is very early on, so you don't see any like grepping, but like early in like Ubuntu's boot, there's a ton of grepping or like change during and stuff like that. But you can see like these programs are starting these programs, and I don't know the name of this program unless it like opens another program. Then it would tell you. No, I take that back. I don't know the name of this program. Oh, no, I do know the name of this program. This program is this, right? I don't know the name of this program unless I trace it back. And eventually you could trace it back, like 9E, here's 9E, so I know it's this program, right? So it's not quite pretty like that. Ideally, what you'll be able to do is just from anywhere in the code be able to tell what program this code belongs to. So for like any memory read and for any memory write, that's what OSI does. In order to do that, we have to pinpoint this task structure in 64-bit Linux, and I haven't quite figured out. I pinpointed the kernel stack. We know it's on the kernel stack. I don't know where it is on the kernel stack. So I've been looking. Well, recently I've been doing much, but I was looking into finding a book that could describe the kernel stack for newer kernels better. I have a book that describes the stack for 2.6, but it's not. It's changed a lot since then, and I parts of it are the same, but a lot of it is different. And that task struct got moved around, and I don't know where it is. And so I've been looking for just like documentation telling me where is this task struct located on the kernel stack. What I'm going to try doing too, I haven't tried doing, is maybe there's a pointer to it that hasn't moved. So I'll try using like OSI's offsets into the kernel stack, and see if maybe I can use one of those to kind of locate some important information that hasn't moved throughout the updated kernels. I also did look into, we were suspicious about 32-bit code still working with OSI, even though 64-bit didn't, even though the new kernels for 32-bit move the task struct. And it turns out that Ubuntu kernel 4.8 is the very last kernel that doesn't move that task struct. So that's kind of like the last one that doesn't move it. And then any newer version of Ubuntu in 32-bit and 64 moves the task struct pointer. So that's kind of the idea, is like right now we want to be able to locate the task struct, and once we do, we'll be able to dump the task struct, and we'll have access to all of the process information we can imagine. And then I think we'd be done with this kind of low level getting information out of the operating system, and can work purely on analyzing the data, or if we come across something suspicious, then looking into why there's that suspicious activity. And it turns out that having this type of background, I think, helped, because we already kind of ran into a couple of like suspicious activities with like CR3 that we could fix, and also suspicious activity with sequential like kernel writes or something like that, where like the process name was being like loaded in by the kernel and stuff like that. It wasn't really suspicious. It was just kind of, it looked like it could be a bug, and it turned out it wasn't. It was just the kernel loading in the process name. I mean, it's there. If you need it, use it. If you don't need it, don't use it. And hopefully I'll probably put little timestamps to different functions in the video, so you can just link to what you need to use or what you want to know about, or you know, you can Slack me and I'll try to respond to it. And like I said, I think what I'm doing right now is just gonna try to get that last try to get this to work with 64-bit Linux, and then from there just kind of put this on the back burner and jump into maybe helping Lynn analyzing the for patterns. The one thing I do want to mention, so there's Meltdown. I account for Meltdown. I do not account for Spectra. So I kind of don't know fully how Linux handles Spectra mitigation. So I can't really account for that. I don't even know if it will affect this stuff that much. So I have to look into that in the future if that's something that we're curious about. But yeah. All right. Thanks for watching. I'm sorry for spending a long time on this, and hopefully it will give you some just insight into what the low-level debugging information we have access to as of now. All right, thanks. Bye.